Hello everyone and welcome back to Integrated Math 3. In today's episode, we're going to be discussing chapter 1.2.2, which is using math models. And the essential question for this section is, how do we make a mathematical model to solve a problem? And so we're going to look at chapters 1-73 and 1-74, and we're basically going to try to optimize and build the largest possible box given that we have a piece of paper that is 8.5 by 11 inches. And the way this box is going to be constructed is we are going to go ahead and, well, I'm going to draw a box real quick here, or a piece of paper anyways. And what's going to happen is, assuming we have an 8.5 by 11 inch piece of paper here, so this is, this will be 8.5, and this will be 11. The way this is going to work is I'm going to cut out little squares in the piece of paper right here. So I'm going to cut out these squares. And when I cut out these squares, what's going to happen is it's going to allow me to erase these little bits right here. And then by erasing the little bits, I can then fold this box or these little edges out into the screen. So these pieces here should be sticking out towards you in the paper. So that is the fundamental basis on how this box is going to work. And so what I'm going to do is I'm going to go and find out what happens if the inches that I cut are going to be these parameters here. So from here, let's say, for example, if I do 1, that means that the square that I'm cutting out is 1 by 1. If it was 2, it would be 2 by 2. If it was 3, it would be 3 by 3, and so on and so forth. We'll go ahead and make a prediction of 4, 5, and 2.5. But let's see what happens if I cut out a square that is size 1. Well, remember, if it's 1 and it's a square, that means that 1s are showing up all over the place. And the consequence of cutting out squares of length 1 are that this 8.5, well, I think you can kind of see it, is no longer 8.5, right? I'm actually cutting out 2 inches from it. So that would be 8.5 minus 2, which would then be 6.5. This 11 here, which used to be 11, is no longer 11. It's actually going to be 9. And so I'll go and fill those pieces in real quick here. So this is going to be 9, this is going to be 6.5, and the height is actually going to be the length of the square, which is going to be 1. Now, if you think about it a little bit here, hopefully it'll make sense, because what happens is that if I fold this guy upwards this way, what happens is that he sticks up out of the screen 1 inch. And so now from here, in order to calculate volume, well, that's just going to be length times width times height. So if I just do 9 times 6.5 times 1, I end up with a total volume of 58.5 cubic inches. And so now what I'm going to do is I'm going to go and pause for a little bit, and I'm going to go ahead and fill in the rest of this, because honestly, I don't think I want to waste your guys' time with you all watching me figure out what each of these are. And so I'll go and pause for a little bit, and I will fill the rest of this in, and I'll be right back. And we are back now with all of the dimensions. And so what we're going to do is just kind of see if these match up with what you have on your paper. Hopefully it does. Now, I left the 5 purposely blank because technically if I was to do this robotically without really thinking, I actually would end up with a negative 2.5 right here, because I'd really be subtracting the 10 from the 8.5, and so unfortunately that's not really going to work, right? Because what happens is that I can't end up with like a negative space, so I should end up with some kind of negative number, and that's just not going to be how we do it, right? I end up cutting out more box than I already have, which is why the 5 actually is not even possible to begin with. All right, and so hopefully that makes sense as to why the 5 wasn't doable. So if you had trouble with that, then it should make sense. So what I'm going to do now is I'm going to go ahead and try and create a function of volume so that if I input a particular side length that I'm going to cut out, I can find out what that volume is. And so what I'm going to do here is I'm going to scroll this guy a little bit to the right, or maybe I'm just going to create some more space. Hang on, I'll be right back. Okay, I think I've resized just enough, so I'm going to go ahead and move over here. And so again, I'm going to go and just redraw this image here. And whoops, change colors here. So I'll go ahead and do this in yellow. All right, so from here, if I go and redraw this piece of paper, now I'm going to go ahead and look at it in a different way. So instead of drawing and cutting out a particular size, I no longer know how much I'm going to be cutting off of this thing. And if I don't know how much I'm going to cut off, I'll go ahead and call it a variable. And that's going to make this guy worth X amount of inches that I'm going to be cutting off. Again, I don't know how much I'm going to cut off. It's just going to be worth X inches from here. So from here, again, that 8.5 that we used to know of as 8.5, he's really 8.5 minus 2x. Same thing with this 11. He's actually 11 minus 2x, right? Because I'm cutting out 2 x's from either side. And so what that does is it creates a volume formula of 8.5 minus 2x times 11 minus 2x times the x, which is the height of this piece of paper. Now, what I'm going to do here is I'm actually going to go to Desmos, and I'm going to graph this image right here. So I've actually kind of already done it. And so here it is, x times all this stuff. Now, of course, the order in the multiplication on Desmos is not the same as the one on the screen. However, multiplication order doesn't matter, so I think I'm good. Let's go ahead and zoom out. Now, notice if I continue to zoom out, I get this graph that looks like this. It goes up and then down and then up. So what I'm going to do next is I'm going to try and figure out a proper domain and range for this particular function. So I'm going to go and put that prompt into the screen real quick. I'll be right back. Okay, now that we're back, I'm going to go ahead and draw a quick little sketch of this thing. It kind of looked like this, pardoning any drawing capacity, but kind of looked like that, right? And so from here, it says, what part of the graph makes sense in the context of this problem? Well, this point right here is happening at x equals 4.25. And so the way I figured that out is I actually went to Desmos and I clicked on it. Right there, 4.25, 0. Now, if you think about the way this box actually works, or the way this box is going to be constructed, anything, right, this is the v of x axis, which means that this axis, the y-axis, represents the volume of the box, which means anything below the y-axis represents negative volume, which really can't exist in the real world, right? So with that in mind, I'm hoping it makes sense that the window for this box would be up until the first x-intercept, because this is all possible positive volumes of the box. And so from here, the reason why that's helpful is because it helps us establish a domain. Well, the domain of this thing in interval notation would start off at 0 and it would end at 4.25. Now, again, we're still new to interval notation, so the brackets are both hard in this case because we actually can be on these points on the graph. So I think that works. The range should be from 0, which is the lowest that the graph is, all the way to the top, wherever this point is. I don't know where that is just yet, but I'll go and just put in a bracket right there because I know I can get there. Now, to figure out how high up that is, I'm going to go ahead and go back to Desmos one more time, and that looks like 66.148. So I'll go and load that into there. So 66.148. And now it says give an estimate for each of the questions based on our graph. So it says, what size square should you cut out to maximize the volume? Well, the max volume, hopefully it makes sense that the max volume actually shows up right here at the tip of this curve right here, which occurs at 1.58. And the y-coordinate of that is, again, that 66.148. So hopefully the size of the square cut out would be 1.58. The dimensions of the biggest box possible would be what happens when I take 1.58 and when I plug it into my v of x function. So that's going to be, if I set it up here but don't solve it, it's going to be 1.58 for the x times 11 minus 2 times 1.58 for the length, and then the width is going to be 8.5 minus 2, and I need to change colors here because I'm about to go off the screen, times 1.58, like that. And when all is said and done, those dimensions, after you calculate this, and you will need a calculator for this portion here, it ends up being 7.8 by 5.3 by 1.6. And what I did, I just rounded from here. I rounded this to the first decimal spot. And then if you multiply these three things together, you end up getting a maximum volume. So the max volume is going to be 66.148 or 66.15 if you decide to round. So hopefully that makes sense, the notion of using a math model, and in this case by model what we mean is we mean the equation, the volume equation that you should have had from the previous handout, or the previous part of this handout. That is the mathematical model that we use to calculate the best possible volume for this box given these dimensions. So I think that will wrap it up for this lesson here using the mathematical model. I will go ahead and ask you to please leave questions or comments in the comments area, and I will answer them when I can. I will see you all in the next episode.